Трансляция идет, но давайте подождем еще 2 минуты до 10 часов. Трансляция идет, но давайте подождем еще 2 минуты.
Такое эхо, что ли?
Это я включил трансляцию, забыл выключить звук.
А,
Там запаздывание в трансляции.
понятно.
So, dear colleagues, let me open the plenary session. 2 talks will be given during the session. My name is Alexey Yegorov. The session is chaired by me and by Professor Gromova. Екатерина Викторовна, please.
Good morning, dear colleagues. Let me introduce myself. I am Ekaterina Gromova, and I will be a chair with Alexei instead of Elena Parilina for today's 2 plenary talks. Let me introduce the first speaker. It's my pleasure to introduce him, Leon Aganesovich Petrosyan. He is the Dean of the Faculty of the Applied Mathematics and Control Processes, and also he is the head of the Department of the Mathematical Game Theory and the Statistical Decision. We know Leon Aganesovich as a leading scientist well-known all over the world in the field of game theory, and his research interests lie mostly in the field of dynamic setting of the games, and including non-cooperative and cooperative setting. And today Leon Aganesovich will focus in cooperative setup of the dynamic games, and his title of the talk is on the strong time consistency of set-valued optimality principle. Please, Leon Aganesovich.
Thank you, Ekaterina. Yes. Okay, so we can start. Here is the outline of my talk. First of all, I have to explain what I mean under strongly time consistency. This term has meaning only in the field of n-person differential games. I will explain that in classical control theory, there is no need to introduce this notion. Also, I will focus on some special cases like repeated games, associated zero-sum games, and multi-stage games. At the end, I come back to time consistency and strongly time consistency and bibliography. Okay, let's go. Oh, sorry. So first, I try to explain the notion of strongly time consistency. let M be a fixed point in n-dimensional space, and consider classical control problem, control problem 1, which is written here. We have the point X from n-dimensional space, and using the control U, we have to bring this point on the time interval t0, t big, as close as possible to the point M. So we have to find the control U dash t and the corresponding trajectory x dash t, such that at terminal instant, the distance between the terminal point x dash t and the point M will be minimal. This is a very classical control problem. We shall denote this problem by gamma x0 t minus t0. It is important to underline that the problem depends upon initial conditions. And denote by c x0 t minus t0 the reachability set of the system 1 from the initial point x0 at terminal time t. For control theory is very well known what it is, but anyway, I shall explain. So C x0 t minus t0 is the set of all points which can be reached from the initial point x0 t0 exactly at time t big, exactly at the end of the process. For simplicity of our illustration, which is not very important, but just to make a nice pictures, I suppose that the point M doesn't belong to the set C. That means that we cannot reach this point exactly during the time t big. Now, let's look on this picture. Sorry. So we start at x0, yes, and we have this reachability set C x0 t minus t0. It's like oval, this big oval, yes. This is the set of all points which we can reach exactly at moment t big, and we start, and we have to come as close as possible to the point M. You see the point M is down, is picked down. So suppose the line x0 m dash is the closest point from this set. Of course, our optimal trajectory, which gives us this solution, is going from x0 to m dash. You see this line, yes? Now, what is very trivial and well known in control theory, that if I am at moment tau on some intermediate moment, I am on this trajectory, and I decide and suppose I forget that I already solved the problem. I forget, and I solve it once more. Then I will come to the same point m dash. This is very, very trivial from the point of view of control theory, but very non-trivial in game theory. So this means that the solution is time consistent. That means that the rest of the control starting from x dash tau to m dash is the part of optimal control of the whole trajectory from x0 to m dash. This is trivial. But another point which is not so trivial is that suppose in point x dash I found another optimal trajectory, which is here in dash line, which comes also to m dash. It's possible. There may be many optimal trajectories. Then it is also very well known in control theory that if I start from x0 and come to x dash and then switch to a new trajectory, then I will come also to the same point m, closest to the point m, the m dash point. Yes. M prime, to the point m prime. I've come to the same point. That means that we can formulate it in the following way: that any optimal prolongation of my motion, starting from the initial condition on the initial optimal trajectory, will give me, together with the start which I have done, will give me the optimal trajectory in the whole problem. So I can always switch at each time instant. I can switch to another optimal trajectory, and I will not go out from my previous optimal solution. This means strongly time consistency or strongly dynamic stability. So this is true for control problems. It's well known. I think you know, everyone who does control theory knows. But let's change the problem a little bit. Change problem. This. Okay, sorry. Now consider slightly more complicated problem. The motion equations are the same, but the aim of our control is different. It is necessary to come as close as possible to the system of points, not to one point, but to a system of points, M1, MK, where Mi belong to Iran. Denote as before the problem in the same way, and see the reachability set, and suppose also that this reachability set has no intersection with the convex closure of the set M. Also, this also is done for simplicity of presentation. Is not important, not very important point. Now, as optimal solution in this case, we shall consider the Pareto optimal set, which will be the projection of the set M, the convex sum of set M over the reachability set. Let's see this on the picture. It's like this. So you see, so the system of controlled equations are the same. Reachability set is the same. The motions are the same. But the aim is not to come to one point, but to come as close as possible to, in this case, 3 points, M1, M2, M3. Then the Pareto optimal set is the projection of this triangle on the reachability set. What is Pareto optimal set? Well, is well known. I will not give down the precise definition. This is how, in some sense, the best points, in the sense that no one from these points is better than the other. It's closer to all three points as the other. So this is this set. If we have the problem to minimize distance between a number of points, then as usual it is very natural to consider Pareto optimal solution. So AB, the red line, is the Pareto optimal set, is the projection. Now let's start moving. Suppose I start moving to this point M dash, this one of Pareto optimal points. Of course, I have to select one point to go to one point from this Pareto optimal set. How I select this point is another problem, a very big problem. Many thousands of papers are written on that. But suppose I know how to select. So I'm going to M dash. But in some intermediate time, tau, it came in my mind somehow that let's check whether I'm going the correct way or not. And then I construct a new reachability set, which is smaller, Cx dash tau t minus tau, which is smaller, of course, because less time remains, is smaller. And I compute a new Pareto optimal set. And I see that the new Pareto optimal set is different. A dash, B dash is very bad. This is very bad. And one of my friends said, why you go to M dash? Let's go to M2 dash. I can't say anything against. They both are Pareto optimal. But if I go to M2 dash, then starting from the beginning, if I have some memory, I hope that we all have memories. If I have some memory, I will see that from the point of view of my initial problem, this point is not Pareto optimal. That means that here happens what doesn't happen in classical control theory. So the optimal prolongation in the sub-problem starting on the optimal trajectory is not optimal in the whole problem. If we connect this with the motion which I start from the beginning. And this means that we lose strongly time consistency, or this strongly dynamic stability. So in a very simple case, already we lose it. But the time consistency remains, dynamic stability remains. If I continue going from X dash to M dash, then this point remains Pareto optimal. In this case, it's not very bad. So if I continue the same way, then I still follow the same optimality principle, the same rule. So this is the example when the optimal control is time consistent or dynamic stable, but not strongly dynamic stable. The very simple case. Now let's see what is going in more complicated situations in the games. This here is written what I just told, everything written. Yes. Oh, sorry, coming back. So we see that the new control U cap, which consists from the previous control on the time interval from t0 to tau, and the new control U2 dashes on the other time interval, where U2 dash leads me to an arbitrary Pareto optimal control in sub-problem. This new control, which I constructed, U cap, may not be Pareto optimal in the whole game, in the whole process. So we lose strongly time consistency, which means that in this case, the optimal continuation, the optimal continuation of the motion in the sub-problem with initial conditions on Pareto optimal trajectory, together with initial Pareto optimal motion, may be not Pareto optimal in the original problem. This means that the Pareto optimal solution is time consistent, but not strongly time consistent. Now, how to come out from this problem? What kind of outcomes are possible? This is a very simplified example. We take just the simple motion. We have three controls. Each control is less the value of each control by modulo is less than 1. So the time is fixed. So the retrievability set is just the cycle, is inside the cycle, and the points M1, M2, M3 are here. And the first Pareto optimal set is AB. What may I propose? What comes to our mind? In the beginning, let's go to some Pareto optimal point X dash. Then after some time, I see the new Pareto optimal set, which is A dash B dash, and I consider all motions which are possible if I direct my motion to this new Pareto optimal set, and I can do it practically in every time instant. And if I make a set of such motions in which in every time instant I direct my motion to one of current Pareto optimal points, then I get a big set of solutions. Of course, these solutions will be not Pareto optimal in the previous problem, but they will be in some sense. They can be introduced as in some sense optimal solutions. I can introduce a new solution concept. Let's do this way. At each time instant, we have to follow the direction to some of current Pareto optimal points, not necessarily the previous one, to some of current points. This is like I would say this in Russian, like колеблемся вместе с партией. Also, we change our solution dependent on what's happening around. Then the new solution will be this dashed region. This will not Pareto optimal, will be dashed region. But this solution, it can be proved. I proved this, I think, in 1983, this publication. This is strongly time consistent. This is very interesting. That this solution, which seems somewhere anecdotal, yes, but is really very good one, is strongly time consistent. So following the current situation is strongly time consistent solution. But just an example. Let's go forward. Now, I will not speak about Nash bargaining. Let's skip this. It's very special and not so introduced, not so interesting. Now, I want to fix my attention on cooperative differential games. So we have the motion equations, 2 x dash is equal to 1. So we have here, instead of k, I have to write n. This is a mistake. So I have n players. The right sides of equation of my equation 2 is controlled by different players. And the payoff function is given like this, which is a function also of controls, but actually it depends upon only trajectory, but trajectory depends upon controls. That's why I'm writing ki as a function of controls. Yes. And what is the idea of cooperative game theory? The classical cooperative game theory. The players choose such behavior which maximize the sum of their payoffs. And then the problem is how to divide this sum between the players. And so I introduced the so-called cooperative trajectory, which maximizes the sum of the payoffs. Suppose that such the trajectory is this. This is a classical control problem. Of course, thousands and 10,000 of papers is written about this, but this problem is solved. And I denote this by V x0 times 0 n. So this is the maximal total payoff which the players can get when they play together, when they try to maximize the joint payoff. The problem in cooperative theory is how to divide this payoff between the players. To introduce this possible this method of optimal division of the payoff, we have to introduce the so-called characteristic function V x0 T 0 S. So we take arbitrary coalition of players S, yes, and I have to explain this. What is characteristic function? This is not written here on the slide because it's known game theoretical term, but since I'm giving a lecture not only for game theories, I have to explain this. So Vx0 T 0S is the maximal payoff which the players from coalition S can guarantee themselves if playing alone. Also in the worst case, if other players are playing against them. So how to compute this value? This is a big discussion in cooperative game theory. So there are different approaches how to compute it. This can be a solution of zero-sum game between coalition S and n minus S. So in the worst, so we can consider this V as payoff in the worst case scenario when all other players are enemies of S, are playing against S. There are other approaches when we suppose that coalition S is playing as one player, the left out players also form a coalition N-S, and they play between each other the game and they find the Nash equilibrium. But then it's not known which Nash equilibrium. There may be many Nash equilibriums, and as we know in game theory, the outcomes in different Nash equilibriums is different. So how to define characteristic function is a big problem. But suppose we follow one of the ways of this definition, the classical one, which was introduced by John Feynman, Neumann, and Morgenstern in the beginning of last century. So this is the max mean solution in the zero-sum game between coalition S, which tries to maximize his own payoff, and the coalition M-S, which tries to minimize the payoff of coalition S. The payoff of coalition S is the sum of the payoffs of his members. Then, if we have this function if we have this function, we can introduce the so-called set of imputations. Ex0 t minus t0. What is set of imputation? You see, this is a vector psi, which components psi I is, such that the sum is equal exactly to v. What was v? Let's come back to our previous slide. V here in formula 3 is the maximal total payoff which the players can guarantee themselves. So we suppose from the beginning that players act as one player and just maximize the sum of the payoffs. So the problem is how to divide this. So we see that this the sum of the components of vector psi is equal exactly to v. Yes, but also there is another condition: vi is more than v x0 t minus 0 I is more than this. This means that we consider only such kind of vectors psi which in the sum give us the total maximal payoff, but each player gets psi I is the amount which is supposed to be given to player I. We suppose that the player I gets at least as much as he can get if he plays alone against all other players. So because v here, you see, v x0 t big minus t0 I is the value of characteristic function when instead of the set S we have one player I. So this is the guaranteed payoff of player I when all other players are playing against. So we consider this type of set, the so-called imputation set. So we allow to divide the maximal total payoff this way. So the first is that we have to divide the whole payoff. The whole maximum payoff. We must not leave anything outside, and each player has to get at least as much as he can get by playing alone against, in the worst case, if all others plays against him. Now, you remember that we introduced the reachability set of the system 1. This is C t big by t0 x0. This is the set of all points which can be reached exactly at the moment t big. And consider for each initial condition from this set, consider a subgame with duration t big minus t small, yes, of this our game. So actually the point y is the point where we can come at moment t small, and then coming to this point y, we are starting a new game because we have still the time t big minus t small left. The new game. This new game is gamma y t minus t. This is called subgame of the game. For this subgame, we can construct the same characteristic function, and also the imputation set, the same imputation set. Now, the important thing is the so-called optimality principle. Optimality principle is how to divide this total payoff. We have this set of imputations 4, which can be also considered as optimality principle. But because the sum of this v, the sum of v in 4, the vi's, vx0 times 0 I in 4, the sum, if we make summation over I, so is much less than the total payoff maximal which is reached, then this set is a very big set, is infinite set. And the problem is which imputation is the best. So it's not sufficient to say that I am dividing the total maximum payoff and I give to each of players at least as much as he can get himself. Maybe he can get himself only 0, but they all get some millions of dollars. So there is a huge amount of possibilities to divide this million between the players. So the problem still remains how to divide this V, this total payoff. But of course, under the condition that this partition, this imputation must satisfy the condition 4. And we introduce the so-called optimality principle C. So for each subgame, for starting from initial state y, and with the duration t minus t small, for each such subgame, we introduce the optimality principle C, which is some subset of imputation set. This is important to understand. So the optimality principle is some fixed subset of the imputation set 4. There may be many, in classical game theory, there are many different optimality principles. There are set-valued optimality principles. About these set-valued principles, I will speak today. Set-valued principles, also Pareto optimality is also set-valued. But set-valued principles they are not uniquely defined. So we call optimal the whole set. So each element of the set is optimal. Of course, they are very different, but they all are optimal. We call them optimal. But there are also single-valued solutions, the so-called Shapley value. But today I will not speak about Shapley value, because in the case of Shapley value, there is no necessity of strong determined consistency. No ideal is necessary for strong determined consistency. Now, suppose C can be core or an M solution. Unfortunately, I didn't give here the definition of the core, so I can just show. I don't know, you see or not? Okay, after I will do. Good. Now let's go forward. Now, what is the most important thing? We decided to get the maximum total payoff. To get the maximum total payoff, we have to follow the so-called cooperative trajectory. The trajectory which is resulting from our optimal control, which maximize the sum of the payoffs. I denote this trajectory by x-t. This is the cooperative trajectory. Now, when moving along cooperative trajectory, I am in each time instant, I am in the sub game, in the new game, which starts from this, which starting point on this trajectory, and the shorter duration t minus t big. And in this sub game, I can always I can do this. So this is the sub game along the cooperative trajectory. And in this sub game, I can once more compute the set of the imputation set and the solution, which also is a subset of this imputation set, which depends upon this t. And we see that these sets are changing when t changed. Because suppose if, let's come back for a moment. You see, this is the imputation set, yes? And you see here the sum, the sum of this, of the components of vector psi is equal to v, which is function from initial condition and duration. And also this inequality, the right side, is function of initial condition and duration. That means if I'm moving along the cooperative trajectory, then these parameters change, because in the subgame I have a new initial condition on the cooperative trajectory and the duration is different. So the set itself is changing. And the same is true also for the solution concept. So yes. So I'm considering, so this now suppose I took some solution from my optimal solution set. This, remember, we define the solution in cooperative game as some subset of the imputation set. So this is, suppose I start the game, and in the beginning we agree with all players. We agree that we have to choose this imputation psi. So we have to, each of us know, I will get psi 1, you will get psi 2, Ekaterina will get psi 3, Alexei, you psi 5. Suppose in the beginning we already decided, in the beginning of the game, we decided. But when the game develops, these sets change, and this solution, which was selected by us in the beginning from the optimal solution set, is also must be somehow changed. And I introduced, this was 1979, the so-called IDP, imputation distribution procedure. So the way how to distribute this psi, this optimal solution, during the time. This is like salary. How much I have to pay to each of the players so that they still stay on the cooperative trajectory. They did not want to go out to find better way of life. There is the beta, this is input IDP, the imputation, the instantaneous payments to the player. This is the total sum. This psi is vector, of course, but if we take components, then the beta IT is the instantaneous payment to player I when moving along cooperative trajectory. Now, but what condition must satisfy this beta? What condition must satisfy this beta? And this is the so-called dynamic time consistency or dynamic stability condition. It is very important that if the payments are made during the time, then at time instant t small in the sub game, you see that in the sub game we already got till moment t, we already got this amount. So suppose the time is 30 year time, and this t is 10. So in 10 years I already got this salary, and this is what remains, what I have to get after this time t, what I have to get. So this is very important, that what I have to get will remain optimal in the sub game. So I have to follow the same optimality principle as it was in the beginning. So this beta, this payment state, this current payments must be organized in such a way that the rest of the payment remains optimal in the same sense as the previous. This is called time consistency of dynamic stability. If it holds, then the solution concept is, if I can construct such beta for every psi, then the solution is called time consistent. Of course, sometimes it's not possible to make these betas positive. Sometimes they must be negative. That means that in some time I will not get any salary, but I have to pay myself. But the life is like that. This is mathematics. I can't go out of this. Unfortunately, the life is like that. Now, let's go forward. Now the strongly this was time consistency. Now the strongly time consistency is a little bit more different and difficult definition. Now, remember the example with Pareto optimality. Remember the example. We started move our motion along Pareto optimal trajectory, and in some moment we change this. We may change this our Pareto optimal solution to another current Pareto optimal solution in the current subgame, and together it was not Pareto optimal. This was bad. I don't want that this happen in this case. That's why I introduced this condition. What this condition means? It means, suppose till moment t, I got this. This is this is a vector because beta is vector. Yes. But if we speak about the components, this is the, if I take right here I, then this is the component. So this is the amount, the vector which shows the amount which each player gets till moment t, using the IDP, imputation distribution precision. Now, consider the current solution in the current subgame. In the current subgame, which starts from t and has the duration t big minus t, this current subgame. Then it is necessary that if in this time instant t on competitive trajectory, someone or we all together decide that we shall not follow our previously selected solution. Previously we said we want to make psi. This was solution which we selected from the beginning. But we say, why you have to follow this? We are all revolution people, we like revolutions. There is another solution here. There is a whole set. Why don't take another solution? It's also optimal. Why you have to follow that terrible dogmatic solutions? No, we want to make revolution. And so if I require that if we select another solution from the current optimality principle and add this to what we already get, we still remain in the optimal solution of our game. This is a very important property, which is called strongly time consistency. So this symbol means that if A belongs to Rn and B to Rn, then A plus B. This is the set of all A plus B. So this is one vector, this is another vector. The sum is equal, belongs to this. This is the strongly time consistency. So if this condition holds, then it allows me to change at each time instant, to change my previously selected optimal solution, but in the optimal way, not in any way, in the optimal way. And then it altogether will be still optimal. This is very non-trivial. It doesn't happen in real life, but it's very non-trivial. But how to do it? How to make how to construct some new solution concepts that this will hold. So since, as it is well known, time consistency of comparative solutions taken from the classical one-shot game theory takes place only in the very special cases, it is clear that strongly time consistency is a very special event. Not that strongly time consistency has sense only for multi-valued, set-valued optimality principle. This is also very important, that this solution has sense, this definition has sense only for set-valued solution concepts. Because if it is single-valued, then this will be actually a single tone, and we have a usual time consistency. This solution will be the same time consistency. This will be equal to this. This for Shapley value is coincide with usual time consistency. Okay. Now, first, what I supposed is the transformation of characteristic function. So I introduce for any characteristic function which was introduced in the beginning in the classical game theory, I suppose this transformation. This is very so-called integral transformation, which is very natural, looks very natural. So you see, this is here written the value of characteristic function in the subgame, which starts from moment t till the end of the game. This is the current payoff, the current total payoff of all the players if they follow the optimal trajectory, which maximizes the sum of the payoffs. The current at each time instant t, the current, and this is the total maximal payoff which the players got in the subgame. So this proportion VXTS over V Tn is the, how to say, the proportion of the power of coalition S. So what proportion takes the coalition S from the total payoff? So I propose to pay at each time instant to members of coalition, not to pay, but to consider as their guaranteed payoff for players of coalition S, the proportion of the instantaneous payoff proportional to the power of this coalition. So in each time instant, instead of paying just the sum of the payoffs, I pay them. I change the formula and propose to make these guaranteed payments as proportion to the power of this coalition in the whole game. So in the sub game. So this and it's easily seen that if I introduce this type of characteristic function, then the total payoff will be the same. So it's only a redistribution of the payoffs. Now we can define the core under this new characteristic function. This core is one of the solution concept, and make the same linear transformation of the imputations. We introduce this imputation. You remember what was the imputation? Imputation was the just I come back to this was the imputation. Yes, this was the imputation. This is the vector which assigns to every player what he has to get at the end of the game. This how we divide the total payoff. Each one gets psi I. Now I change this definition. In this way, I use some current imputation, and I divided the instantaneous payoff proportional to this current imputation, and this is the density function. And by integrating, I get a new imputation. This is also belongs to imputation set. This now. And using this new characteristic function, I can introduce the new solution concept. Any solution concept which is not known in game theory, because in classical game theory, all solution concepts are based on characteristic function. I introduce a new characteristic function, and actually I change all the solution concepts according to this characteristic function. Now it's interesting. What are the connections between the new core, the new solution concept, and the previous solution concept? Yes.
Leon Aganasovich, time is almost up. So
No.
5 minutes. 5 minutes left.
5 minutes. Of course, I have 5 minutes. Yes, I know. Yes, but what is important that this new solution concept is strongly time consistent. And this I can prove. This is very important. But what is the connection between this new solution concept and the classical solution concept? To have this connection, I introduce this formula, which is the maximum of the ratio between maximum of the ratio of the power of the coalition S to the power of the whole coalition. When the game develops, this ratio changed, and this can change in a very strange way. It's not monotonic, but I just take maximum. Yes, and we can see this. There are these inequalities, and this is very important, very important quantity that I introduce the so-called subcore, some part of the previous solutions. This is the new solution, the new imputation set. which is defined by this inequality, which is very similar to the core, and it happens that this set belongs to the intersection of the classical core and to the new core. And this set is strongly time consistent. So this result gives the connection between the new linear transformation of characteristic function, between the new solution, which I introduced using this new characteristic function, and the classical solution. And it happens, which is very non-trivial, that this intersection, if it is non-void, can be constructed and is strongly time consistent. So we have, if this will be not void, then in our classical solution, we shall have a subset which is strongly time consistent. So this is one of the ways of introducing strongly time consistent solution concepts, which is very important for further development of differential and person differential games. So if my time is over, the other slides, they are not about differential games and not control theory. They're multi-stage games and not so interesting for our for members of our community, for our conference. So if I can finish if you want. Thank you very much. If you have questions, there are questions.
Let us thank the speaker, Leona Ganesic. Thank you for the talk. So some questions or maybe comments now. We have a few minutes to do it. Any questions? So may I ask question, Leona Ganesic? So you consider the situation that only one switching may happen along the cooperative trajectory, yes? No. Strong time consistency assume that only once we may choose another solution from the optimality principle. But if we will do it again once more and so on.
Well, you see, I'll show you now. Just come back. I show this. Now I show. Okay. Exactly this. If you consider this case exactly. Yes. So here, actually, I constructed the new Pareto optimal set, not really Pareto set, the new solution concept, which actually is constructed from solutions which switch to each time instant to the current Pareto optimal solution. So if I come, for instance, how I come to some given point here, the trajectory which leads me here has the property that at each time instant, the direction of this trajectory is directed to some current Pareto optimal point. And these points may be different. In each time instant, there may be different points. And this solution is totally time consistent.
Okay, but if we switch once,
yes,
then we will follow this trajectory till the end of the game.
Yes,
if we decide to switch once again,
also we come here. That this is the set of all possible outcomes. If we switch at each time instant, all possible endpoints. Well, I say колебаться вместе с партией. At each time instant, we switch to current optimal direction, which is said to be optimal at this moment. They may be a whole set, but we can switch to any of them, and then we get this. And this is a very optimal, very good solution. We must not laugh about this. This is a very good solution. We have to follow the current situation. And you can switch each time. This example, but in general also the same. So the strongly time consistency exactly means this, that the whole solution is constructed in such a way that if we switch in each time instant, we still remain there.
Okay. So if it's possible, if the final, not final, the current subset C will be not less, but coincide with the initial set C.
What, please, once more. I don't hear. Please.
Может быть такое, что вот эти подмножества в течение подигры будут не уменьшаться, а совпадать с изначальным множеством?
Нет, нет, yeah, of course. Нет, конечно, они уменьшаются. They're smaller and smaller, because at the end point, there will be just 1 point.
Yeah. In general.
Yeah, of course. At the end, will be just 1 point.
Yeah. Okay. So maybe other questions or comments, dear colleagues? If not, let us thank speaker again. Elena Ganashis, thank you very much. Could you switch off the screen?
So now we have a break, 6 minutes break before 11, and then we have the second plenary talk of Vladimir Zvan. Okay.
Okay. Dear professor, you could switch on. You can share the screen now, if you wish, before your presentation.
I am looking for the button. I don't see it.
On the bottom.
No, they do not appear.
Владимир Германович, вот если зайти в Zoom, то там внизу зеленая такая кнопка демонстрации экрана. Ну, у вас как-то по-другому?
Я знаю, где эта кнопка, но сейчас ее не видно.
А вы вошли в Zoom или вы сейчас смотрите на презентацию?
Подождите.
Да, видно.
Да, сейчас.
Да.
Чтобы все было в порядке.
Только вас не видно.
Ну, меня не видно. Подожди. Вы меня слышите?
Слышим, да. Презентацию видим, а ваша камера видим.
Подождите, сейчас
Вот.
видно, так?
Да.
Да, все хорошо.
Потому что кнопки уже наверху. Ну, значит...
Так, подождем еще 3 минуты.
Ну, конечно. Я попробовал, если могу управлять слайдами. Можно.
Алексей, вы дадите, да, знак, когда начинаем?
Да.
Тогда. Ага.
Можно?
Нет, еще 2
Нет,
минуты.
еще пока рано.
Пока.
Вас сначала представит Екатерина Викторовна.
По моему телефону еще 2 минуты, а по ручным часам 5 минут.
2 минуты. 1 минута уже осталась. Okay, I think we can start. Екатерина Викторовна, please.
Okay, if we can start. First of all,
Let me introduce you, Vladimir.
it's okay with the sound, with everything?
Yeah, I would like to say a few words about you.
Oh,
Okay.
thank you.
So it's my pleasure to introduce our next speaker from Romania, Professor Vladimir Razvan. He is a director of the doctoral school at the Faculty of Automation, Computers and Electronics at Craiova University, Romania. Professor Razvan has more than 100 journal papers and book chapters, and also about 7 books, I believe, which are devoted to the stability of time-lag control systems, applications of Lyapunov methods, instability and stability and stable oscillations in discrete time systems. His research interests include nonlinear system stability, nonlinear oscillations, time lag, and distributed parameter systems. He is a full member of the Romanian Academy of Engineering Sciences. So please, Professor Razvan, you're welcome.
Thank you for the, first of all, for the invitation to deliver a plenary speech, for the nice presentation, and allow me also to express my deepest regrets that because of the health situation, I was not able to visit again St. Petersburg, and your department and also the prestigious conference dedicated to Vladimir Ivanovich Zubov, science personality that I not only respect, I cherish and I admire. My subject is connected with my science interests. It deals with system with propagation. In the Western literature, they are called more or less 1D systems with distributed parameters. 1D means one dimension. That means you have time and one space dimension. The parameters are distributed along the real line or a segment of real line. Or as you would say, these are hyperbolic systems in the plane, as used to say Anatoly Dmitrievich Mashkis. Here I try to summarize some of my experience along of several decades of research and results. First of all, allow me to present you the outline, that is the field of applications, then the basic scientific principle of my research, the boundary value problems connected with functional differential equations, and then some specific aspects, that is to be some as examples of what I will say in general. First of all, lossless and distortionless propagation. Next, the functional differential equation of the drill string, of, I would say, of the distributed parameters drill string. And finally, the research program that I am very interested to present to people who hoping that the ideas will be somehow continued. Now, concerning the fields of applications, I would enumerate some of them. Control dynamics of cogeneration, that is combined heat electricity generations for engineering. Next, control and dynamics of water hammer and frequency megawatt for hydroelectric power plants, control of open canals, and control and dynamics in gas networks. I would add here also the problem of synchronization of oscillators through distributed parameter media in the sense of classical sense of Christian Huygens. But the aforementioned applications belong to the more comprehensive case of controlling systems of conservation laws. And in my paper, I was giving appropriate references. Another class of applications arises also from the dynamics and control of the mechanical systems containing distributed parameters, beams, and rods. And here I mentioned the overhead crane and the marine riser, the flexible manipulator, and the oil well drill string. All these are mechanical systems, and as you will see, they have something in common concerning their model. And to these applications, we shall add two more applications from the field of electrical electronic engineering: the distributed parameters waveguides, which appear at very high frequency electronics, and as I mentioned previously, the synchronization of local oscillators through one-dimensional distributed media. And in the next, we shall show how these apparently variable systems can be approached in a unitary way from the point of view of stability and stabilization. And this relates to our second part of the presentation, boundary value problems and functional differential equations. And I would like to mention first a thing that I mentioned several times. The very first known reference of an equation with deviated argument belongs to Jean or Johann Bernoulli, as you would like to say, in 1728, published in that year, but it has in its rather long title, it's a very long title, the mention of a weight stretch vibrated string with distributed masses on it. I say long time because it is cited like this, Meditationes de cordibus, de cordis vibrantibus. This is in Latin, but nevertheless it was published in the communication of St. Petersburg Academy in the year you see there. It belongs to the period when such great mathematicians as brothers Bernoulli and Euler were employed by the Russian Academy of Science in the time of the great 18th century of Russia. The equation is as follows, and it's important to say that this equation arose from a problem for hyperbolic partial differential equations, And the interesting thing is that someone then mentioned, it's mentioned, I don't know where, that this equation was nevertheless deduced in a wrong way. It's somehow mistaken. But it's important to mention that it arose from a problem of hyperbolic partial differential equations. And more recently, that is in the previous century already, in the papers of Anatoly Dmitrievich Myshkis and his co-workers, there is presented a methodology of associated certain systems of functional differential equations or integral equations to certain hyperbolic partial differential equations with dynamic boundary conditions containing the Volterra operators. The first paper of Myshkis was published, if I'm not mistaken, in 1957. The most important that I know published in Mathematische Sbornik in 1960. But afterwards, from time to time, Anatoly Dmitrievich continued to publish on this subject with co-worker Professor Filimonov, and publications were in the journal Differentialные уравнения, differential equations. This is, it has the priority, the papers of Anatoly Dmitrievich concerning this subject. Nevertheless, Kenneth Cook in the United States and one of his co-workers, I think David Krume, considered a more explicit case to which I will refer because it's easier to follow. They considered, as you may see, the partial differential equations with time-varying parameters, but already in the normal form, that is with partial differential equations with the Riemann invariants separated and with non-standard boundary conditions. You see, they are ordinary differential equations in the boundary values of the Riemann invariants with initial conditions, as you may see. And you have a forward wave and a backward wave in this representation. Now, I would like to refer to their results because they were not proven in a rigorous way. I did this in a very late paper in order to put an end to this question. The idea is as follows. You consider the differential equations of the characteristics, defined in a general way, the two characteristic curves crossing some point of the strip is mentioned here, the space and the time strip. We define the propagation times, which are time varying, as you may see, and mention the possibility of extending these characteristics to the right always, and to the left sometimes for the increasing, and for the decreasing characteristic is vice versa. Now, the progressive wave is written along the increasing characteristic, and the reflected wave along the decreasing one, and we obtain here some representation formulae for the Riemann invariants for the waves using the forcing term and the boundary values. Here I mentioned, you may see in the figure, the two types of the characteristics. One that can be extended on the entire strip, and ones which cannot be extended to the entire strip. You see, this one stops at this abscissa, and these last characteristics will serve to define the initial conditions for the system of associated functional differential equations. Now, as I say here, for the cases when the characteristic can be extended to the left, we can use the representation formula, and to obtain this relation only between the boundary values of the Riemann invariants. And you see, you have here the propagation times, which induce the deviated argument. Now, making these notations that only to simplify the writing, we find that these functions, y plus and y minus, satisfy the following system of equations with deviated argument. As you may see here, it's a system with deviated argument, which has two delays, two deviations. Now, what is with this system? Consider it as an independent mathematical object. Its solutions can be constructed by steps, provided some initial conditions are given, which are defined here using the characteristics, the lower characteristic I mentioned there. And we rewrite 6 in order to have this representation formula in function of this y plus and y minus. And we may state a mathematical result, which I proved completely in a reference given in the paper. If we consider the boundary value problem and a solution satisfying the equations as well as the initial and boundary condition, you see I consider it sufficiently smooth, while ordinary differential equations also have generalized solution, then y plus minus of t defined by 8 are a solution of 9 with the initial conditions defined by 10. Conversely, we start from the system of equations with deviated arguments as an independent mathematical object, consider a sufficiently smooth solution of 9 with a set of initial conditions, then u plus minus lambda and t defined by 11 is a solution of the boundary value problem with the initial condition defined also by the representation formula, but computed at t equals t0. And what I would like to mention for the public interest in time delay equations is that the aforementioned approach represents a rather natural approach of introducing various classes of equations with deviated arguments. If we define the following integers, which defines the maximal k for which the coefficients are non-zero in various equations for non-deviated and deviated argument, according to the sign of this integer, L plus L minus minus K plus K minus under brackets, the system 9, the system of functional differential equations, belongs to one of the 3 classes of systems with deviated argument. If m is larger than 0, it is of delayed type. If m lower than 0, if of advanced type, a very natural way to introduce advanced type. And if m equals 0, is of neutral type. And this assertion I like to mention is consistent with the classification of Georgy Alexandrovich Kamensky, which defined neutral, delayed, and advanced accordingly to the idea of smoothing the solution in time. If it is of delay, it is smoothed in time. If it is of neutral, it remained as it was in the initial conditions. If it is of advanced time, the smoothing is lost step by step. Therefore, it cannot be extended to the right for positive t as long as we want. And as experience shows, my experience at least, most systems with deviated argument are associated to the boundary value problems for hyperbolic partial differential equations are of neutral type. Their solutions are not smooth in time. Together with the propagated discontinuities, this reflects the mismatch between the initial and boundary conditions. This mismatch I would like to mention because we are at a Zubov conference and we are in the country of Alexander Mikhailovich Lyapunov. The initial conditions are always the effect of short time perturbations, and they must be considered arbitrary. Consequently, generally speaking, they are not matched with the boundary value conditions. Now, an application concerning the lossless and distortionless propagation. In the 1D wave equation, which is written here, the general solution is written as it is, with phi and psi arbitrary function. One is wave traveling to the right with velocity c, and the other one is transmitted distortionless and also lossless. The same holds for the backward wave traveling to the right. Distortionless propagation means that we always have deal with a delay but the forward and backward waves don't mix between them. In the spherical waves in n dimensions, read as you can see here, and if n equals 3, the general solution is as you can see here. The transmission is distortionless but lossy because you have a gain which is decreasing, an amplitude which is decreasing with the distance, with the radius. As mentioned in literature, in fact, is the remark of Richard Courant, living in a three-dimensional space is a happy circumstance because signals can be broadcasted without distortion only in 1 or 3 dimensions. The electronic engineering application is a distortionless waveguide, which has these equations, and you see, these are the telegraph equations with only space varying parameters. The line is called distortionless in voltage because in electronics, we look generally at voltage generators and voltage propagation. If there exists a solution, you see, of this form, where F is called attenuation and tau is the propagation delay. They should be, it is mentioned, independent of phi and subject to F of 0 equals 1, tau of 0 equals 0. Introducing the Riemann invariance, we obtain the equations, as you can see here, with the notation of the propagation delay, and it is not possible to obtain distortionless propagation for both waves because look at these terms which make to these equations to be connected one with the other one. So we can reduce only in one equation the term. Choosing this option for the forward wave, A of lambda will be strange enough or interesting enough, subject to be chosen, subject as a solution of this Riccati equation. We obtain this equation, and the distortion, if we want distortionless condition for both equations, we shall obtain exactly the Heaviside matching condition, which is generally speaking difficult to fulfill because it's with equality and the electronic engineering parameters are not always very precise. Now, let me show you another application which will put you another problem. The drill string dynamics. We start from this model of the drill string dynamics. You see, again, we have a distributed attenuation, but we have distributed space parameters, non-conventional boundary value problems because they are described by ordinary differential equations, and with a non-linear condition at the drilling head. This is friction of the drilling string with stone, and it is generally speaking non-linear and a very ugly non-linearity. Here we also can point out a possible distortion propagation. We introduce new state variables to obtain the Friedrichs form of the equations. We introduce the Riemann invariance. We obtain these equations with this notation for A of C, of S. And if A of S is chosen like this, we shall obtain the forward wave distortionless. For space constant parameters, that is uniform drill string, well constructed, distortionless would require also losslessness, since A the differentiated of S equals to 0. Now we shall write down the functional differential equations of the drill string in the case of constant parameters and of identically zero attenuation, because this case allows us to obtain equations with constant delays. The equations look as you see, number 31. We define new variables to obtain the Friedrich forms, introduce the Riemann invariants, which are all, physically speaking, both of them angular velocity, and following the methodology of section 2, we make these notations, following differential and delay equations, but we eliminated variables in equations. The cyclic variable that is the angular velocities, the angular coordinates, which are nevertheless not important in the stationary drilling regime when you have a constant angular velocity. This system belongs to the general class defined for rows, which can be met in my several publications. Unlike the applications there, matrix D in 34 has its eigenvalues plus minus I on the unit disk and not inside this. This means that the difference operator of the neutral functional differential system is not strongly stable, but only marginally stable. A critical case. All applications arising from mechanics and or mechanical engineering are such. Moreover, I discovered one appearing in hydraulic engineering with 2 delays. And this implies additional difficulties in tackling qualitative problems in stability and oscillations, because you have your system would be very sensible to the variations of the delays. Moreover, let me tell you the following. The assumption of the difference operator to be strongly stable, and in our case for D to have the eigenvalues inside the unit disk, was made by Jack Hale at a Congress of World Congress of Mathematics in Moscow in 1966, and was adopted happily by all people working in neutral functional differential equations, because many trouble are left aside. And for this reason, some very fine results concerning the other cases, the critical cases, which were obtained by the students and co-workers of late Lev Ernestovich Elsgoltz at the Patrice Lumumba University in the 60s and 70s, were forgotten in the pages of Soviet Union journals as differential equations or papers of the Seminar of Functional Differential Equations. And in my opinion, such cases must stimulate us to treat these critical cases, because good results, new results, interesting results are obtained always at the boundary of a known domain. Now, I like to mention here one way to overcome the difficulty based on possible available numerical data that I had at my disposal. The time constant assumes that it is small. We reduce it, we take equal to 0. And for this reason, the difference part becomes in this way stable. This means that here is hidden something that we still don't know, reducing the dimension of the system by singular perturbations sends us to a strongly stable system. Here I think, and it's mentioned for all interested people, maybe this reduction of Tm is not legitimate from the point of view of the singular perturbation theory. I am meaning, again, because I am in Russia, that's a stability conference, one has to check for functional differential equations, the Klimushev-Krasovsky type theorems. It appears to me that for some cases, Klimushev, who was a student of Nikolai Nikolaevich Krasovsky, obtained some result published, but I'm not able now to say you where. As you see, now we have both systems. As you see, the system of the fast variable and the reduced systems are, if they are all asymptotically stable, then the overall system follows to be asymptotically stable, provided the small parameter Tm is small enough. How small, this probably will show the proof. I did once upon the time such a proof, obtaining such evaluation, not for this case, but each case must be treated separately. And as I say, this gives reasonable hopes that we can solve this critical case somehow. And now allow me, I hope I still have enough time, to enumerate a research program, some of them which I mentioned in some kind of notebook, and hoping that I will be able to tackle them in the future. Let me tell you that these are refined problems, difficult problems, and usually people in our days are not very eager to work with such problems. My hope is that according to the tradition, the public of the St. Petersburg University will be able to tackle such problems. So, my first observation is that less books and research surveys are concerned with neutral functional differential equations than with retarded one. The book of Bellman and Cook gives a certain extent to the linear equations and their characteristic equations, as the book of Edward Pinney was mentioning that both of them are translated from English in Russian. About neutral equations, you can find nothing in the very first book of Anatoly Dmitrievich Byshkis, neither in the book of Nikolai Nikolaevich Krasovsky. They are considered not only in the book of Elfgoltz and Norkin, or Introduction to Functional Differential Equations, which I don't know if was translated in English. It appears it was translated in English, but also I would like to see they appear in the earlier book of Lev Ernestovich Elfgoltz, published a couple of years after the early book of Myshkis. For the Russian-speaking audience, I can say it's called Качественные методы в анализ, published in 1955. Luckily, I have this book. I don't know if probably in the library you can find here. In the book of Halanai concerning differential equations, stability, oscillation, and time lags, the neutral equations are not even mentioned. But Professor Halanai told me that this book, this last chapter was written in a hurry, as you can say, because he had some purpose of priority, and you understand how it was even in the 60s concerning this. After the three versions of the book of Hale, 71, 77, 93, the neutral equation enjoyed an extended formalized study. Hale, starting from his report in Moscow in 1966, the interest for this class of equations increased. For instance, you may see the books of Vladimir Leonidovich Kharitonov, and the first of them is written also with co-workers. The second one is his book, and I have I may say, because you are his colleague, many of my younger colleagues now in Romania study the time delay systems using his book. And the spread of them or the one-to-one correspondence between the two equations appeared in my book in its Russian edition, and some surveys also contributed to this interest. Is the book of Niculescu, published by Springer, and more recently is a book of Gil, who also was educated in former Soviet Union and works now in Israel. I think he is 2 years older than myself. And I also add here the book of books of Kolmanovsky and Nosov. I mentioned two of them because there are substantial differences between them. The second is not the English version of the first. And other valuable references are the books by Kolmanovsky and Meshkis. Summarizing the references, I can give a list of problems which are waiting for their solutions. We start the problems with the problem of the strong stability of the difference operator that I was already presenting to you, that the assumption of strong stability was promoted by Hale and allowed the construction of the stability theory for neutral functional differential equations in close connection and analogy with the retarded one. Fortunately, all examples people knew have strongly stable operators, unless you have the counterexamples I mentioned to you previously. So, as I told you, is a problem to study, probably because we shall come again to this assumption a little bit later. Another open problem for neutral functional differential equations is the so-called Bol-Perron result. If a forced linear differential system has bounded solutions with zero initial conditions for all bounded input signals, the free unforced system is uniformly asymptotically stable. There are some references in the book of Kolmanovsky and Nosov and in the book of Gil. I am not convinced of the rigor of the proof and if it is not possible to do better. And connected to it is the Persitsky type result. Persitsky, the old, as we will see, Konstantin Petrovich or Konstantin Pavlovich, I don't know. Because you have Sergei Konstantinovich's son also working in differential equations. For linear system, uniform asymptotic stability is always exponential under some boundedness assumption for the coefficients. For neutral functional differential equations, the result is not known. And to end this discussion on linear systems, I would like to mention here the so-called problem of the forced oscillations for the quasi-harmonic systems, which is due to Malkin, and you may see it in the book of oscillation, not the book on stability, the book of oscillations. I give here the pages because you don't have a list of paper references, only citations at each page. And this is a book you may see in the paper, the edition of 1956, not one of 1949. And the idea is to consider forced linear systems with T-periodic coefficients forced by the input vector signals, as you see here. This is Fj of T are T-periodic, and omega j, the angular velocities, and hence the frequency, because they are divided by 2 times pi, and T are not rationally dependent. And this shows you that your signal is almost periodic, but a very restricted class quasi-periodic. They are special case which corresponds to all kinds of modulated signals, at least amplitude modulators in radio engineering. And the problem is it is required to find condition on systems coefficient to ensure existence of a solution of the same form as you may see here, with xg of t being t periodic. In general cases, you have the solution of Malkin. For retarded functional differential equations, the problem was solved by Halanai. For neutral functional differential equations, the problem is unsolved. And finally, another open problem is the validity of the Barbashin-Krasovsky-LaSalle invariant principle in the absence of the strong stability of the difference operator as it was proved by Hale. This invariance principle is the basic of the study of stability when you have what is called weak Lyapunov functional, which has the derivative function only non-positive definite, not strictly negative definite. All Lyapunov functions and functional of energy type are of this kind, as was remarked once upon the time by Chetaev. Well, and that will be all. Thank you for your attention.
Thank you very much for the presentation, dear colleagues. It's time to questions.
I can accept and answer even in Russian.
But we have a YouTube translation, so I'm not sure that we can use Russian.
Можно я задам вопрос?
Давайте.
Владимир, ну, могу на английском, могу на русском, да?
Как хотите, Алексей Петрович.
Спасибо. Владимир, вот как вы считаете, интересен ли анализ дифференциально-разностных систем уравнений с периодическими, ну или почти периодическими запаздываниями? Вот интересно ли для инженерных приложений?
По совести говоря, Алексей Петрович, я не знаю. Единственное место, где появляется периодически, может быть периодически, но во всяком случае запаздывания, которые не являются постоянными, это именно эти, я не знаю термин по электронике, waveguides, волноводов, забыл. В теории волноводов могут появляться периодические запаздывания.
В ускорителях, что ли?
Нет, волноводы – это высокочастотная передача сигналов.
Понял, хорошо. Ага.
Об ускорителях не знаю, потому что, вы знаете, у меня есть некоторая, ну скажем, отсутствует, я не могу, физики это особый мир, я только что вошел в этом мире по делам синхронизации, но я считаю, это хорошо, если это по физике у вас найдутся приложения. Вы знаете, Гильберт это говорил, физика слишком серьезное дело, чтобы ее оставили только физикам.
Спасибо. Спасибо, Владимир.
Let me introduce a bit for translate this for foreign people. So the discussion was about the examples of systems with periodic delay or almost periodic delay. So Professor Razvan says that he doesn't really know the application, maybe only some fields where it can appear. Okay, I also have a question, if it's possible. So many questions, but I ask two. First, about the advanced type systems, time delay systems. Are there some real applications where the PDE can be reduced to advanced type system?
You see, Alexei, The example was this arithmetic property of generating advanced equations with advanced arguments is purely mathematical, but I liked it because it's very natural. To be frank, I am not able now to remember if in the earlier, very early papers published on functional differential equations, you can meet advanced equations with advanced arguments, maybe in electrodynamics, early paper of Rodney Driver. I think I've seen some mention, but you see at that time, Western journals were very rare in Romania, maybe in Soviet Union also. I haven't seen this paper only being mentioned. To be frank, it may happen that these equations will appear on some badly written model sometimes. You see, in my opinion, always, I have written a long paper. Unfortunately, it was buried, as we say, in a less circulated, what I say, sbornik, collection of papers. And I call all this is what we call model validation, or be extended, augmented model validation. You need always to look not only existence, uniqueness, and continuous data dependence. This is well-posedness in the sense of Adamar for partial differential equations, but it works for ordinary also. But you need also to point out invariant sets, for instance, if you have some variables being positive, and even without automatic control, to have some inherent stability. You see, I'm very fond of what is called the stability postulate of Chetaev, which says that only those states, that is equilibrium or steady states, can be observed and measured if they are stable. Otherwise, they are destroyed by perturbations if this is not stable. For this reason, I think if someone will study equations with advanced argument, he must check exactly these things. If I am good in my memory, I met once upon a time a person who was working on equations with advanced argument, was from Poland. His name was Jan Blaž, from Gdansk. He was active in the 60s, and he visited our seminar once upon the time at the beginning in the 70s or things like this. You can meet him. Blaž is written, he published in Russian, maybe you may be able to find his name like this with Russian characters. If it is with Latin, is Blaž with a point on Z. I think he worked on this subject. If there are not references in the book of Elsgolz and Norkin, I don't know where, because by Hale, for sure and certain, you will not find anything on them. You find a lot on neutral, but nothing on, at least some mentions.
Yeah. So mostly, you know, only mathematical results.
Yes, only as mathematics. Neutral, they appear in these problems coming from partial differential equations. I can tell you that to discover is a little strongly put. But when I was writing my PhD thesis, candidatскую диссертацию, Professor Halanai asked me, find on time delay systems, find examples, applications. You are an engineer. And I started to look for applications, and I found 3 papers with such applications published in Inženjerni Zbornik on 46, but the papers were forwarded to this journal before the war. There were two authors, Kabakov and Sokolov. Each of them had one paper, and the third paper was written together. The two of them died or disappeared during the blockade. They were in the operative army, and they did not return. And I was very impressed by the fact that it was written there that this is some kind of homage to the young, talented engineers who died defending their country. I am still now impressed when I remember this. I use their papers trying to understand, and we realized with Professor Halanai that there were neutral equations. He told me, this will be after your dissertation, find other applications. And it were these papers who ignited my interest for such equations, for this corresponding with the equations. In fact, how we discovered that this was neutral, starting from their equations, because everything was linearized. They applied Laplace transform, and they obtained lumped delays, terms of the type E at minus tau s, and this shows that you have delay equations, but the type of the quasi-polynomials showed that these were of neutral type, and then the equations stimulated me to do this one-to-one correspondence, to find it first by Cook and then by Mashkis. Mm-hmm. And since then, all applications I found, they were neutral, due probably to the boundary type of the boundary conditions. It's the boundary conditions who decide the type of the equations. The partial differential equations give you only the propagation.
Yeah, I see. Mm-hmm. So thank you. Another question was, so you showed several examples where you reduce distributed parameter system to neutral type system or retarded type in some cases. Is this common property? I think not. I think not every hyperbolic system can be reduced to time delay one.
No. The simplest case when you have concentrated delay is a case when you have constant parameters. You can separate the Riemann invariants in the two equations, and you will have constant delays. Otherwise, they are mixed. This is propagation with distortion, and you can obtain very strange functional differential equations. In the paper of Mashkis in the last of 60s with Abolinia, published when he was in Riga. Abolinia, how was her name? Velta Abolinia was his PhD student in the time when Anatoly Dmitrievich was in Riga. And they are very strange, but very difficult to manipulate, at least for me, because I wanted also results to understand what was happening in my equations and so on. But even in the paper of Anatoly in his paper, the equations were not separated. They had some part. You had the partial derivative with respect to t, to the time, the partial derivative with respect to the space. All of them were for one wave, because he had several waves. And the other term, the third, had all mixing of the equations. But the functional equations will be of a very strange type, in my opinion, integral differential, or with Volterra operator. Very, very complicated equations. I think no one dared to study these equations more than Anatoly Dmitrievich put some results on existence and continuity.
So the main physical feature to to guess that the system can be reduced to time delay one is the distortionless, yes?
To lump delays, t minus 2. But if you have, let's say, integral terms, perhaps, some distributed delays, then things change. The integral, the distributed delay, in my opinion, can be also a propagation with distortion. I don't know. This is also a problem I like to study. I have some examples on it. It's a paper which gives us something, and I would like to follow it. Strange enough that people who are working now on 1D problems with conservation laws are unaware of these results. Probably they don't like to refer to them and so on. I am just received a book from Springer. Maybe you saw the reference is authorized by Georges Bastin from Belgium and Jean-Michel Coron from Paris on 1D control of 1D hyperbolic systems or things like this. I have it on paper, but it appears to me you can have it on electronic form freely, provided you go to the site Library Genesis and download this book freely. But you'll see no mention on functional differential equations. They prefer to work directly on their subject with operators and so on. For me, functional differential equations are more intuitive, probably because of my experience.
Thank you very much. It was very good talk. Thank you.
You are welcome.
I think the time is over now. If
But,
any short questions or comments, we have a few minutes to do it.
Sorry, I want to ask the professor about if you have a boundary control, how to construct the stabilizing feedback law, for example, for the problem of drilling.
This is not a very difficult question, because all problems I discussed were, in fact, including the control. But I have an old paper on bilinear systems occurring in cogeneration, where I did the synthesis of the control using a control Lyapunov functional, which I am very proud to say I guessed it. My idea is that the Lyapunov functionals have much of them to be guessed. We have systematic and scientific, I would say, approaches to obtain them, but it's also a matter of inspiration. And the idea was as follows. Using a quadratic Lyapunov function, we did with Professor Halanai the synthesis of the controller for the bilinear model of the steam turbine. And then at that time, I was still working in a research institute for power engineering. I asked, what if I take into account the long steam pipe uniting the turbine with the steam consumer? And in this way, I obtained exactly the boundary value problem control with non-standard boundary condition. And I am not able to tell you how it happens that I guessed the quadratic Lyapunov functional. Just I saw it with my imagination. And after one of two small modifications, I was able to synthesize the control, and the control includes in it the integral of the state along the space variable. In fact, for time delay associated equation, it appears a distributed delay, while in the beginning you have only lumped delays. And this is consistent with the theory of controlling time delay systems. If you remember the linear quadratic optimal control for time delay systems, the results of Krasovsky, of of Lee, and many other, of Delfour and Meter, you start with lump delays, but the optimal control includes in it a distributed delay, which is integrated.
Thank you.
So it is possible to do this also.
Thank you.
Okay, maybe one short question. If not, let us thank again the speaker for the talk and for the productive discussion.
I thank you once more. It's
Yeah.
interesting to have such a plenary with interested people, with interesting discussions. And I am open. You can write to me for information, to send you PDFs of papers if you like, even to meet with me on Skype, if you like, to discuss even in Russian. I am open.
Thank you.
Thank you.
So long.
So, thank you. Bye.
Bye.
Bye, colleagues.